Welcome to this presentation, key new Mathematica features for Wolfram SystemModeler. My name is Malte Lenz, and this presentation is going to be about how you can get the most out of new Mathematica features in combination with SystemModeler features. So here is an overview of what this presentation is going to contain. There's going to be a section about control systems, how you can use those in Mathematica to interact with SystemModeler models. There's going to be a section about how you can use new visualization and interactivity features in Mathematica, how you can use new signal processing features, as well as how you can use new time series features together with SystemModeler. In this section, we're going to show how to get a model from SystemModeler into Mathematica by linearizing it, then designing a PID controller for that model, and then getting it back into SystemModeler to simulate it with that controller. For this, we'll use this DC motor model, which has an input V that governs the voltage in the circuit that in turn turns the flange in the motor. And we want to regulate the speed of this motor. So what we do is we linearize the model with WSM linearize, which gives us a state space model in Mathematica. We then design a PID controller for the motor with the new Mathematica feature PID tune. We just feed the system to that function and we get a PID data object back. And we see the parameters it has chosen for our PID controller as well as what tuning rule it used. We can then get back those parameters from the PID data object and feed them back into SystemModeler with WSM set values. We can then show the complete model with PID controller in SystemModeler by calling WSM model center of this model. We see that we have our DC motor, which was the system we saw earlier. We have a PID controller, we have a reference signal, and then we have our disturbance signal, which adds load on the flange of the DC motor. And finally, we have an output motor speed, which shows the speed of the motor. So that brings us to our next section, the visualization and interactivity section, where we're going to show how to use interactivity and real-time simulation to simulate this motor model with our PID controller and disturb it dynamically with a gauge from Mathematica. So we start a real-time simulation of this motor speed model. We add a disturbance or a load controlled by a manual gauge, so a horizontal gauge. You can see that we can slide this slider here on the gauge, and it varies between -1 and 1, and it changes the disturbance variable. Then we use set inputs to set the inputs for our simulation con, which we started up here. And we set the disturbance or the load parameter to this disturbance variable from the gauge. Finally, we do a real-time plot of both the speed of the motor, the disturbance we're controlling with our gauge, and the reference signal. Now we're ready to start our simulation. We do that by pressing play on our simulation. We see the blue line here is the speed of the motor. It follows the green reference signal pretty well, and we see our disturbance, which we control with our gauge down here, the orange one. And if we slide our disturbance, we can see that if we slide it slowly, we don't see the motor speed varying from the reference signal at all, while if we go very quickly, add a lot of load changes quickly, we see that the motor speed actually wobbles a little until the controller kicks in and gets it back to the reference signal. Our next section shows how you can use filter design or signal processing in Mathematica together with SystemModeler models. So for this, we're going to assume an external input to a model that has been modeled with a Wiener process in Mathematica. And we're going to sample that process with by just randomly sampling it and retrieving a time series of this process. And if we plot that sampled process, we see a pretty noisy signal which we want to filter with the low-pass filter. To do that, we use a manipulate of a Butterworth filter, and what we do, we have these two parameters to the Butterworth filter and omega, and if we can tune these parameters interactively and see how the model reacts or how the filter reacts. So in blue we see the original noisy signal, and if we tune these parameters, we can live see how it changes the orange signal, which is the filtered signal. So we're going to choose some parameters like this, and we're going to switch to the next slide to get this filter into SystemModeler. So we're going to create a state space model from this Butterworth filter G, which we had in our manipulate, and we're just going to call WSM create model, which creates a model called tuned filter with this state space model we just designed. We can then simulate our filter with the input of our noisy process E. And then we can plot the results, the input and the output to the filter, and we see that it has the given result, which we could see earlier in the manipulate, but now we have a Modelica model or SystemModeler model which we can apply to any noisy signal like this. In this last section, we're going to show how to use time series and time series forecasting to predict future energy production costs using a SystemModeler model and real-life input data for historic oil price from Wolfram Alpha. So we start by retrieving data from Wolfram Alpha for the daily spot oil price, and we get that data for and sample it with a period of 1 week. If we do that, we get this curve of the spot oil price data, and we see that it has its peaks and valleys, but there seems to be an upgoing trend overall. Then we're going to use this data to make a forecast for 13 weeks into the future after this data finishes, and we're going to use time series modeling to do that. So we will use time series model fit on our data with a seasonal Sarima prediction. Then we're going to use time series forecast on that model to get a forecast into the future, and finally we can plot the result, and we get almost the same curve as before, but with some added forecasting at the end, and we see that the forecast says that the oil price is going to rise after this time. Finally, we can use our forecasted data as input here, input U, to our SystemModeler model, the input controlled electricity production, which models electricity production costs based on oil price. So if we simulate that, we can then show the fuel cost per megawatt hour by plotting that and adding a line here from where we started to predict data. So up to the dashed line is the real data from Wolfram Alpha, and after the dashed line is based on the data from our time series forecasting. And we can see that our energy production cost will actually rise as the oil price is predicted to rise after our cutoff point. We also will have an increased fuel cost for our oil power plant. This presentation just showed a couple of the different ways you can benefit from new Mathematica features in conjunction with SystemModeler, and thank you for listening.